All right, today we're going to dive into the really wild side of chemistry. We're going to meet some of the most reactive, unstable, and, believe it or not, some of the most useful particles in the entire universe.
So everything really starts with this one big question. I mean, just think about it. Everything from the plastic in your water bottle to the medicine in your cabinet. Chemists are kind of like master builders, right? They're constructing these enormous, really intricate molecules from teeny tiny, simple building blocks. So how in the world do they do it?
You might think it's all about careful, gentle assembly, but the real secret? Well, it often lies in a bit of controlled destruction. It's all about unleashing just a tiny bit of chaos to create something brand new and stable. Let's see how that works.
To really get this, we've got to meet our main character. This is a particle that's so reactive, so unstable, that we're basically calling it a molecular outlaw on the run. Okay, so this outlaw's official name is a free radical. Now, in a normal, stable, law-abiding molecule, all the electrons are neatly paired up. Atoms are happy. But a free radical, it's fundamentally incomplete. It's got this one single, unpaired lone wolf electron, and it is absolutely desperate to find a partner.
So this particle's profile is what makes it so fascinating. It is deeply unstable and hyper-reactive. Its entire existence is driven by just one goal: find another electron to pair up with. It's so desperate, in fact, that it has zero activation energy. That's the little push of energy most reactions need to get started? Well, a free radical doesn't need it. The moment it bumps into something it can react with, it just does. Instantly, no hesitation at all.
So, if these things are so chaotic, how on earth do chemists actually use them? Well, they become molecular matchmakers, harnessing all that instability for their own purposes.
And the whole process often starts with an accomplice, a metal atom. You see, metals like sodium are naturally electropositive. Their whole deal, chemically speaking, is to give away electrons to become more stable. And chemists? They take full advantage of this generosity.
So here's the strategy in action. A chemist takes a stable molecule and introduces it to a metal, let's say sodium. The sodium atom eagerly donates an electron, and that forces a bond in the molecule to snap, creating a free radical. Now, if you do this twice, you create two of these molecular outlaws, and left with no other options, they immediately find each other and pair up, forming a brand new, bigger, and much more stable molecule. It's chaos, totally harnessed for creation.
Okay, let's look at another technique and see how this whole idea builds. Instead of making these outlaws one by one with metals, what if? What if you could trick them into creating each other?
This is the brilliant idea behind a free radical chain reaction. It all starts with initiation. A little burst of energy, saved from UV light, creates the first few radicals. Then comes propagation. Each new outlaw attacks a stable molecule, stealing the electron it needs, but in doing so, it creates a new outlaw in the process. This cycle just feeds itself, running on and on and on, until, finally, termination, when the last few radicals find each other, pair up, and the whole chain comes to a halt. So here's the really crucial point. While unleashing this chaos is incredibly powerful, true mastery for a chemist comes from controlling it with insane precision. And to do that, you have to know, not all outlaws are created equal. This is where chemists get to choose their tool for the job. You could use a chlorine radical, which is like a sledgehammer. It is so wildly reactive, it will just smash into a molecule almost anywhere it can, creating a total mess of different products. Or you could use a bromine radical, which is more like a scalpel. It's less reactive, it's more stable, and because of that, it is way more selective. It will patiently wait to attack the one single specific spot on a molecule where it can create the most stable free radical possible.
And the difference in precision here, it's absolutely staggering. I mean, when reacting with certain molecules, a bromine radical is over 1,600 times more likely to attack the most stable position versus the least stable one. 1,600 times. That isn't just control, that's microscopic surgery.
So here it is, the big takeaway. The free radical, this thing that seems like a dangerously unstable particle, is actually one of chemistry's most powerful and fundamental tools. By understanding its desperate nature, chemists can control the chaos. They can turn that incredible instability into a precise engine for building a molecular world that's all around us. This whole principle of using a chaotic, high-energy, unstable state to build something new and orderly, it's not just for chemistry. It's a fundamental pattern we see all over the place. So the final question is, where else do you see it? Where else is chaos harnessed to create order?